Hello, AP Calculus students. It's Mr. Ford here with another summer packet tutorial. This time we're into topic R, and we're into one of my favorite things to talk about, which is basic right-angled trigonometry. In the original draft of this document, there was kind of a line drawn saying that topics A through Q would be due at a certain point, and then R through V would be due later. And that is because at this point we've entered officially into the trigonometric range, which is a set of skills that you probably did not learn in Algebra 2. You probably learned them somewhere along the way in pre-calculus. You could, in theory, start calculus. You learn how to do calculus and then add this stuff in later as you go. But what we're going to do here is we're just going to do topic R. I'm going to go ahead and explain everything to you in as best I can. If you have no idea what I'm talking about, you have a whole kind of time to figure it out. But hopefully this is a thing you're kind of familiar with. It might be a little differently presented just because of the way math curriculums can differ and math teachers can differ. But hopefully after this video, you feel a little more confident in just your basic kind of right-angled trig skills. So let's just start with number one. I'm not going to do notes off to the side today. I'm just going to jump into it because we're going to explain everything as we go. So question number one, if point P is on the terminal side of theta, already we got a lot of vocabulary coming our way, so let's think about that. Terminal side. Find all 6 trigonometric functions of theta. Answers need not be rationalized. All right, we're going to break all that instruction down. Let's start by just plotting the point negative 2, 4, because that is the idea here. We want to think ahead about this since that is a point in the second quadrant. We'll just kind of sketch out a second quadrant graph. We're going to go back 2 spaces and up 1, 2, 3, 4 spaces. You know, with a lot of this drawing stuff, that is point P. The more accurate you draw it, the better it will make sense on your head. Now, with trig, what we're going to do is we're going to make a right triangle out of this information. We always make a right triangle by connecting, first of all, the origin up to that point. So we got kind of our diagonal line. And this is what's going to be called the terminal side of angle theta. Terminal refers to the fact that when you're talking about angles, you're talking about rotation. You always start along the positive x-axis and then rotate counterclockwise. And where you end is what is referred to as the terminal side. Terminal, for my friends that are in Spanish, you might know the word termina, which means end, and it's the exact same language thing there. The terminal side is where the angle ends. So that is the angle in question. It's an obtuse angle between 90 and 180 degrees, or, since we deal with radians, pi over 2 and pi, but we don't really need to care about that because the right triangle that we're going to draw is going to be this one. We always connect our right triangle back to the x-axis whenever possible. And so, even though our angle is technically this angle, theta, we're always going to think about this reference angle right there when it comes to finding the sines, cosines, tangents, and so forth. Speaking of which, we are going to need to figure those out. We're asked for all 6 trigonometric functions. So that means you got the main ones. You got sine, cosine, and you got tangent. We will find those 3 right now before we go any further. Sine is real. In this case, it's really easy because if you're looking at the sides, we already pretty much know everything. We know this side is worth 2. We know this side is worth 4. It's probably a good idea to make sure that's negative 2. And it is. It does count as negative 2 because we're in the second quadrant. And the hypotenuse we're going to have to find by doing just a little quick Pythagorean theorem calculation there. In this case, 2 squared is 4 and 4 squared is 16. So 4 plus 16 equals c squared. And c is the square root of 20. Which we are going to do ourselves a favor and simplify a little bit. Since 20 is 5 times 4 and the square root of 4 is 2, we're going to think about this as 2 square roots of 5. Now, I'm hoping that this process right there is not too much of a stretch for you. That's the kind of thing that with practice, you'll start doing it real fast in your head. For the meantime, just pause the video and think about it for a minute if you're stuck on what I just did. All right. Let's rock and roll. Now that we know all 3 sides of the triangle, honestly, our work is really easy. All we got to do is pick out which side we're looking for. Sine is the opposite over the hypotenuse, so 4 over 2 roots of 5, or 4 over the square root of 20. Honestly, it doesn't matter. The cosine is the adjacent over the hypotenuse. That is negative 2 over 2 roots of 5, or negative 1 over the square root of 5. I suppose we could divide the 2 out here also and go 2 over the square root of 5. For tangent, tangent is the easiest one. It's the opposite over the adjacent. That is 4 over negative 2 or negative 2, like that. Real simple. Now, the reason why I think it's easiest to do those 3 first is because we also have to talk about their partners, their reciprocals. So that would be the cosecant of theta, the secant of theta, and the cotangent of theta, often lined up in a grid like this. Now, you could memorize something like the fact that the cosecant is going to be the hypotenuse over the opposite side, but the easiest way to think about this is take these existing sines, cosines, and tangents and flip them. And it helps when they're in their simplest forms. So the cosecant, for example, is the square root of 5 over 2. And the secant is the square root of 5 over negative 1, or just negative roots of 5. And the cotangent will be negative 1 over 2, or negative 1/2. There you go. You flip them upside down to make the reciprocal happen. That is the answer, the best answer I can give you for this particular problem. If you didn't bring out the 2 out of the square root of 5 and you just left it as square root of 20, that's fine. You did not need to rationalize anything for this problem. Again, I hate to use the word should in these videos, but you should be familiar with these 6 functions coming into the class. And if you're not, it's okay. We have time to build those skills. I certainly never want to ever gatekeep calculus. Calculus is a very powerful mathematics, and you have time to think about other stuff outside of it. So, okay, there you go. There's your sine, cosine, tangent, cosecant, secant, cotangent. Let's talk about another one. One more thing about this problem. I hope you recognize that the fact that we're in quadrant 2 means that our cosine and our secant were negative numbers because of the negative opposite side, or negative adjacent side, rather. Let's try another one. This one's in quadrant 4, which I can tell because the x value is positive and the y value is negative. So we're going to sketch it really quick. I do not know what the square root of 5 is. I know it's somewhere between 2 and 3. So I'm just going to go 1, 2, and a little more, negative 2. So I'm going to put a point out here or so. I'm going to call that there's our right triangle. Again, the angle is actually this because you always start on the positive x-axis and rotate counterclockwise that way, and you end, your terminal side is right there. Of course, we're really just going to focus on this right triangle right here. Of course, we know that this side is the square root of 5, and this side is negative 2, which means that our remaining side is going to be the square root of square root of 5 squared plus negative 2 squared. And that is nice. It's the square root of 5 plus 4, which is the square root of 9, which is 3. That will make our answers much easier. So again, once you've got this work done, now it's just a matter of making out this little grid that we always make and thinking about our sines, cosines, and tangents. So the sine in this case, again, is opposite over hypotenuse. That's the negative 2 over the 3, so negative 2/3. Nothing to worry about there. The cosine is the adjacent over the hypotenuse, the square root of 5 over 3. And the tangent is the opposite over the hypotenuse. We could have done this one right away. Negative 2 over the square root of 5. Tangent is always equal to x over y, y over x. So if you have an xy pair, like we have in this problem, you can easily just do the tangent right away. I gotta zoom out so you can see that y over x thing. That's the thing. And cotangent is x over y. So those two you can usually clock off right away if you're thinking about this. The thing about trig, while I'm mapping this out, the thing about trigonometry is that there's a lot of really simple stuff happening here. It just is all happening at once. Like the negative thing. The fact that this is in the 4th quadrant is just, it should make sense that the sine is negative and the cosine and tangent are both positive. The tangent is negative. Oh, was the tangent negative over here? Tangent was negative over here too. Whoopsie. Sorry, it should kind of make sense that the cosine is positive, but the tangent and the sine are both negative. Anyway, again, there's that word should. Cosecant, secant, cotangent, we're just going to flip these 3 answers. It'd be negative 3 over 2, 3 over the square root of 5, and negative square root of 5 over 2. There you go. There's your 3 answers, or 6 answers. So far, so good. Again, which quadrant you're in, what's positive, what's negative, those are always things to think about. But for the most part, we're just doing a little bit of right triangle nonsense here. Let's talk about some more challenging questions here. Question 3. I always like these kind of questions. I like to like a little puzzle. So the cosine of theta is negative 5 over 13, and it's in quadrant 2. And our objective here is just find the sine of the tangent based on that information. Well, let's draw a picture. They told us it's in quadrant 2. So let's draw a picture of quadrant 2. It doesn't have to look exactly correct. And the cosine, we should remember, is the adjacent over the hypotenuse. It's the ka in ka toa. So that means that we need to draw a right triangle whose adjacent side is -5 and whose hypotenuse is 13. And the reason why the adjacent side is -5 is, well, twofold. First of all, it's in quadrant 2. And second of all, the hypotenuse is always positive. It has to be. So our triangle is going to look something like this. It doesn't need to be super accurate, but, you know, -5 and 13. That fits what we're looking for here. So the sine is going to require the sine and the tangent will both require that missing side. So let's figure this out. Now keep in mind that's the a, I suppose. A squared plus -5 squared equals 13 squared. You might recognize this Pythagorean triple here. It's going to be 12. If you don't know that, I'll prove it right now. A squared is equal to 169 minus 25, which is 144. And that means that a is the square root of 144, which is 12. 5, 12, and 13 make a Pythagorean triple. So that means that the rest of this problem is pretty trivial in my opinion, because now that we know all three sides of the triangle, the sine is 12 over 13 and the tangent is -12 over 5. All we got to do is grab the appropriate two sides off the triangle, and that's that. Let's try number 4, which is a little bulkier though, because you got a cotangent out of nowhere and it's in quadrant 3. You might notice that your cotangent is positive. Tangent and cotangent are both ratios of x to y, and they are positive, therefore, in quadrants 1, where x and y are both positive, and in quadrant 3, where x and y are both negative. But I'm getting too talky. Let's take a look at it. Let's draw quadrant 3. Now, cotangent is not a ratio that we use very often, but we should just remember it's the reciprocal of tangent. Tangent is the opposite over the adjacent. So this is the adjacent over the opposite. It's the reciprocal or the flip of the original tangent. So we need to draw a right triangle whose adjacent and opposite sides give us those two numbers. I have no idea what 2 times the square root of 10 is. Is it more or less than 3? That's a good question. Well, the square root of 10 is a little more than 3, so 2 times that. So there's approximately a 2-to-1 relationship. I just want to make sure I draw this kind of accurately. It's going to look something like this. Now, what's important here is that the x and y's are actually both negative here because we're in quadrant 3. So this is -2 roots of 10, and this is -3. I think I got that right. The adjacent side, yeah. This would be the cotangent because the regular tangent of this would be 3 over 2 roots of 10. Perfect. Now all we got to do is figure out the hypotenuse. So let's set up a little Pythagorean theorem problem here. We need to do -2 roots of 10 squared plus -3 squared, and that will equal c squared. So when it comes to -2 roots of 10 squared, well, -2 times -2 is 4, and square root of 10 times square root of 10 is 10, and 4 times 10 is 40. So this is 40, plus 9 equals c squared, which is a suspiciously perfect square number, which means that c is 7. Very cool. And now the rest of the problem is simple. Sine is going to be -3 over 7, and the cosine is going to be -2 roots of 10 over 7. Notice how the sine and the cosine are both negative, therefore the tangent is positive, since tangent can also be defined as the sine divided by the cosine, which we'll talk about in another video. Okay, now we have just a handful of are these true or false questions. State in which quadrant is the following true. I think to answer these questions, we should just draw a general diagram, because we don't really need a lot of room to answer these questions, because we're just going to answer them with which quadrant. So this is going to be a thing to think about here. Remember that any point up here in quadrant 1, let's label our quadrants, 1, 2, 3, and 4. This is kind of a crash course in basic trig today. So any point in quadrant 1 is going to be a positive followed by a positive. Any point in quadrant 2 is a negative followed by a positive. Any point in quadrant 3 is negative, negative, and any point in quadrant 4 is positive followed by negative. With that in mind, it doesn't matter where. Let's draw a little circle on this. Might call it a unit circle from your trig days. It doesn't matter where your triangle or where your point lands. Any ratio, for example, Doesn't matter where the point is, but if you're in quadrant 1, the sine is the opposite over the hypotenuse, and so the sine is positive. What's worth mentioning, in quadrant 1, all of the ratios are going to be positive. That's important. Now, if we jump over to quadrant 2, let's just draw kind of a right triangle over here in quadrant 2. What you have to remember about this right triangle here is that the opposite side is positive, but the adjacent side is negative, and the hypotenuse is always positive. So what this means is that the only ratio that will stay positive is going to be the sine, since the sine is a ratio of the opposite to the hypotenuse. So sine and subsequently cosecant are greater than 0. Or I guess I'm being consistent, I'll say plus. Sine and cosecant are positive, everything else negative. Now if you dip down into quadrant 3, again draw a little right triangle down here, now you've got a negative adjacent side and a negative opposite side. This means, and your hypotenuse is always positive, this means your sine is negative over positive, negative. Cosine is negative over positive, negative. But tangent is negative over negative, which is positive. So in quadrant 3, we're fond of saying that the tangent, and of course therefore the cotangent, is positive, and everything else is negative. In quadrant 4, one last one of these to talk about. You might see the pattern happening already, but in quadrant 4, again, you've got a positive adjacent side, but a negative opposite side, and of course the hypotenuse is always positive. So here, the sine, negative over positive, that's negative, but the cosine is positive over positive. We saw that up in number 4. So down here, we're fond of saying that the cosine, or the, and of course that means the secant also, is positive. Now, the acronym that helps you remember this is ASTC, or all students take calculus. Ha ha ha, clever. This tells you which trig functions are positive in which quadrant. That's how you think about that. In quadrant 1, they're all positive. In quadrant 2, just the sine. In quadrant 3, the tangent. And in quadrant 4, the cosine. All students take calculus, ASTC. It's a pretty clever thing. Now, with this diagram in mind, these questions will become really easy. So, first question, where is the sine positive and where is the cosine negative? Well, sine is positive whenever the y value is positive. Here's another entirely different way of thinking about this problem. The sine is positive whenever the y is positive, since sine is the y value and cosine is the x value. So sine is positive in quadrants 1 and 2. Cosine is negative whenever the x value is negative, and that is true in quadrants 2 and 3. And so, of course, the marriage of these two groups is quadrant 2. If you have an angle whose sine is positive but whose cosine is negative, you're in quadrant 2. How about question B? Where is the cosecant less than 0 but the cotangent greater than 0? Might be worth putting sine down here and tangent down here, since they have the same plus-minus relationship, since they're just reciprocals of each other. So where is the cosecant or the sine negative? Well, that happens whenever the y value is less than 0. That happens in quadrants 3 and 4. Cotangent is positive whenever the tangent is positive, and that happens whenever the x's and y's have the same sign. And that happens in quadrant 1 and quadrant 3. And so the marriage of these two groups is quadrant 3. And of course, for last question here, when is the tangent positive, which we already talked about in the last question, happens in quadrants 1 and 3. And when is the secant less than 0? Again, it might be helpful to just think about cosine there because they have the same relationship. Well, again, the cosine is negative whenever the x value is negative. That's in quadrants 2 and 3. And again, the marriage of this group must be quadrant 3. And there you go. I hope this was helpful to you, especially this last little part. This last little part is just something to really be aware of whenever you're dealing with any trigonometric functions, especially when negatives and positives play up. Again, I'm of the opinion this is a really simple idea, but it all comes at you all at once in trig. It's all in giant waves, so it can get overwhelming really fast. Just take some practice to make sure you're going through those steps slowly and surely and understanding why the answer is what it is, because with trig, the real key is to understand why the answer is what it is, because you can draw a picture, as I hope I'm demonstrating so far for these problems. You can draw a picture for anything in trig if it's ever confusing to you. I hope you guys enjoyed this tutorial there. I hope it was of use to you. From here on in this series of videos, it's all trig. In the next, we got to talk about special angles that we should be aware of around the unit circle. This is probably the only one that you need to know to be successful in AP Calculus. So hopefully all this stuff is helpful. It is always useful to remember what a sine or a cosine actually is, and you'll be fine. So I will see you in the next video. You know what? It's summer break. It's going to be 85 degrees today. I hope you guys are having a great time. Hope you do something fun today. And I'll see you in the fall. I'll see you in the next video too.